This video is going to look a little bit different than the other videos in this playlist. What I'm going to do now is I'm going to work through a mixed bag of questions on complex numbers. Now the idea is when you get here, you've already worked through complex numbers and you've got an understanding of complex numbers and how they work. So this video is going to take a bit longer. The idea is that you already have the background knowledge, so I'm going to place questions up. A recommendation would be that when you see this, you see a clean page, you pause. Then you try it yourself just to test to see where you are. So it's going to be a mix. It's not going to cover everything that we've done on complex numbers, but it's going to be a mixed bag of questions just to see how can you deal with various questions on the same overall topic, but smaller details that differ. Can you deal with them? So please don't just watch me do complex numbers and do exercises on complex numbers. Rather, pause, try it yourself, and measure your own progress. So let's get started. Here's the first question. I'm giving you two complex numbers, Z and W, in rectangular form, and I'm asking you to do a calculation. Now, generally, if I give it to you in rectangular form, you can keep it in rectangular form and use those for calculations, with one or two exceptions, which we will look at. So if I look at Z minus W over W, I'm given Z and W, so that'll be 4 minus 2I minus 3 plus I, everything divided by W, which is minus 3 plus I. So that will be 4 minus 3 is 4 plus 3, so that's 7. And my imaginary part, I've got minus 2I minus I, so it's minus 3I over minus 3 plus I. Now, there's no definition for division of complex numbers. As we saw in one of the previous videos, the way we divide is by multiplying top and bottom with the complex conjugate of the denominator. So that's minus 3 minus I. So by multiplying the numerator and the denominator with the same number, it doesn't change the value. So now we've got two multiplications, one in the numerator and one in the denominator. Now this technique makes our denominator quite simple. We're going to end up with 9 plus 1, which is 10, and you can check that. But if I multiply a complex number with its complex conjugate, I end up with a real number. My numerator, if I multiply it, I get, for my real part, minus 21 plus 3I squared, so it's minus 21 minus 3, so it's minus 24. And then the imaginary part, I've got 9I minus 7I, so it's plus 2I. So you can represent this answer in a couple of different ways. If we just have it in pure rectangular form, that's minus 12 over 5 plus 1 over 5I. All right, next one. Given U is equal to A plus BI, I'm given Z and W, and I'm given an equation, so a relationship between these three complex numbers, and we want the values of A and B. So we want to figure something out about U. Now there's a trick to this. If you simply substitute U, Z, and W into this given equation, you're going to end up with a big mess. There's going to be simultaneous equations that you have to solve to get to A and B. But with a quick change of subject of the formula, if I'm after U, I'm after the A and B. So let's get U alone on that side. That means U is W minus ZW divided by Z. Now you can simplify that further if you want, you don't have to. But from here on, now I've got U alone on one side. That's the number that had the variables in. So first change the subject of the formula and then you substitute in. So W, I've got minus 4 minus 2I minus Z is 3 plus 6I times W, which is minus 4 minus 2I, everything divided by Z, which is 3 plus 6I. All right, so I've got minus 4 minus 2I minus what is Z times W. You can simplify that one. You will have minus 12 plus 12, so it's not the real portion. The complex imaginary portion is minus 24 minus 6, so it's minus 30I over 3 plus 6I. So that gives me minus 4 plus 28i divided by 3 plus 6i. Now, similarly to the question up top, multiply the numerator and the denominator with the complex conjugate of the denominator. And in my denominator, I'll have 9 plus 36, which is 45. My numerator, the numbers are getting a bit big. 12 plus 28 times 6, that's 156. My calculations are correct. And then I've got 28 times 3 plus 24, I've got 108i. Right, and that you can simplify and rewrite as 52 over 15 plus 12 over 5i. So here are the next questions. It's all related to one number we're given, different types of questions about that number. Now the first thing to notice is this z is not in rectangular form. It's in the form of a product. So before we can do anything else, we need to simplify and get z in rectangular form. So we'll have z is then equal to minus 2 root 3i. And we've got plus 4i squared, so that's minus 4. So if I just change the order, because we're used to writing it like that, minus 4 minus 2 root 3i. So let's look at what we're asked. The first question is the imaginary part of z. Now, z is made up of a real part and an imaginary part. So just to remind you, if z is equal to a plus ib, a is the real part and b is the imaginary part. So the imaginary part of z is just the number that's associated, attached to the I. The I isn't there, and that is minus 2 root 3. So two things. Don't write the I there, because that's not the imaginary part. The imaginary part is just that B portion. And secondly, that's an exact number. Don't give decimals, because then you're going to have to round off. Right, the next one, determine its complex conjugate in rectangular form. Now, yet again, if you worked with Z in this form, you wouldn't be able to do anything. But as it's given there, the complex conjugate is just going to be minus 4 plus 2 root 3i. And then the third portion asked, write Z in polar form, using the principal argument. So to write Z in polar form, that's r cis theta. I need the r and I need the theta. Now we know the r is the square root of a squared plus b squared, so that's minus 4 squared plus minus 2 root 3 squared. Now note, to go back to z, do not use the complex conjugate, because I'll get the wrong argument. Right, and that gives you root 28. Yet again, leave it exact, leave it like that. Don't give decimals. You can simplify that a little bit if you want, but for now, just leave it like that. Now to find the angle, first check which quadrant it is in. Negative real portion, negative imaginary portion, so I know it's in the third quadrant. So to find that principal argument theta, it's arctan of b over a, which is minus 2 root 3 over minus 4. But that'll land me in the first quadrant, so I must minus pi from that to get the principal argument. So that gives me, with a bit of calculator work, you see that ends up with an irrational number, ugly decimal number. We stop there. That means this is the principal argument, the exact value. So how do we write z? Z is then in polar form root 28 cis that angle theta. Now it's an ugly angle, or it doesn't look nice written like this. So those minuses cancel out and the 2's cancel out if you want. That's root 3 over 2 minus pi. But this is the exact value. So if you have to work in exact values, this is what z looks like. So don't round off if you're working in exact values. So let's move on. Yet again, look at the question, try it yourself, and then unpause and see if we're on the same page. Okay, we're looking for z. We're told z times a complex number is equal to another complex number. So this is a quick and easy one. Z is then I plus 2 divided by 3 minus 2i. And yet again, practicing the division of complex numbers, we multiply and divide by the complex conjugate of the denominator. Top and bottom, multiply and divide by the same thing. All right, so my numerator, let's start with the denominator. It's 9 plus 4, so that's 13. That's a nice one. The numerator, I've got my real portion is 6 minus 2, so it's 4, plus my imaginary portion, we've got 3i plus 4i is 7i. And there we go. We can write that as 4 over 13 plus 7 over 13i. All right, next one. There's 2 questions here. Pause, try it yourself, and let's see. The first one, let z be equal to 1 plus I. Compute and simplify. Now here's a complicated question. We're told to leave the answer in rectangular form, and that's just a little hint to tell you don't change it to polar, leave it as is. So what would that look like? Well, this is just calculation based. So it's 5 times z squared. Now z squared is just z times z divided by z plus 1. Well, if I add 1 to z, I just have 2 plus I. So that's what we want to calculate. So firstly, 5 times 1 plus I times 1 plus I is 1 minus 1. So the real portion is 0. The imaginary portion is I plus I is 2I over 2 plus I. So we've got 10I over 2 plus I. How do we divide? By multiplying the numerator and the denominator with the complex conjugate of the denominator. You should be good with that one now. By now, the denominator is then 4 plus 1, which is 5, and my numerator becomes 20i, and the real portion is 10. So it's 10 plus 20i. And if you're not sure how I'm getting to these numbers, please go back to look at the videos on multiplication of complex numbers, so that we can tidy up a little bit, and we can write it as 2 plus 4i. And there we go. Next question. Give the principal argument of this complex number. So now we must just figure out what are we doing here. We're given a complex number and it seems to be in polar form, and we know in polar form I've got r, I've got theta, so I've got the argument there. So when they ask for the principal argument, what we need to look at is the argument that's given. On the argand plane, 7 pi over 6 is a full pi and another pi over 6. So it's over there. This number z is over here. It's not the line, it's just the point. But I'm just drawing the line so we can see where it ends at 7 pi over 6. Now we know that a principal argument, principal argument, is between pi over pi and minus pi. So we want the principal argument to be between there. But we also know the polar representation is not unique. So this polar number is exactly the same as root 3 cis if I measured my angle in this way round. And that is minus 5 pi over 6. So these two complex numbers in polar form are identical numbers. The second one is just written with the principal argument. And so we can generate, by adding and subtracting multiples of 2 pi, full circles on the argand plane, we can generate an infinite number of representations for this one. But we're asked for the principal argument, so the argument of z, capital A means the principal argument, is minus 5 pi over 6. Now, very important distinction here. This does not mean that 7 pi over 6 in any way is equal to minus 5 pi over 6. Those two angles are not equal. The one's positive and the one's negative for starters. What do they share? They share a terminal side. So that's all they have in common. So don't make the mistake to think because these polar numbers represent two representations of the same numbers. And in rectangular form, you can change them to rectangular form and see it's exactly the same number. But this does not mean that the angles are the same. They simply have the same terminal side. All right, now we're looking at raising things to a power and finding roots. The last portion of complex numbers De Moivre's that looks at finding powers and finding roots, and not to get confused. Now, if at all we're asked to find z to the power something, z squared is still all right, because you just multiply it in rectangular form with itself if it's given in rectangular form. But any higher power becomes complicated to repeatedly multiply the rectangular form. So what we do is we change it to polar form and we use de Moivre's law. Much easier. But now here, please notice that this z is not even in rectangular form. So we've got to fix that first. If I multiply it with minus 2i, I've got minus 2 root 6i minus 2 root 6 times I squared, so it becomes plus 2 root 6. So if I just change the order to get it in the standard way we used to, so it's 2 root 6 minus 2 root 6i. All right, now we're not finding z to the power 4 yet. We're first changing it to polar form. Now this z is located in real portion is positive, imaginary portion is negative, so it's in the fourth quadrant. So our modulus, the r value, is the square root of 2 root 6 squared plus minus 2 root 6 squared. And that would give you root 48 or 4 root 3. Right. The angle is simply arctan of b over a, so minus 2 root 6 over 2 root 6. And that gives me minus pi over 4. So we can change this z to polar form. 4 root 3 cis minus pi over 4. Now we use de Moivre's law. Z to the power 4 is 4 root 3 to the power 4 cis of minus pi over 4 times 4. And that gives me 16 root 3 cis minus pi. There we go. Next question, yet again, raising a number to a power. This one's even more deceiving. You want to multiply the rectangular form 3 times. Much easier to change it to polar form first. So if we had to change that number to polar form, let's first see where it's located. Both the complex, the imaginary and the real portion are negative. So it's in the third quadrant. The modulus is the root of minus root 3 over 2 squared plus a half squared. That should give you a very nice modulus of 1. Then to find the principal argument theta, and we prefer to use principal arguments, that'll be arctan of b over a, so it's minus a half, lots of fractions here, over minus root 3 over 2 minus pi to get you into the third quadrant, and that'll give you minus 5 pi over 6. So this calculation is the same as raising 1 cis minus 5 pi over 6 to the power 3. And to do that, it's 1 to the power 3, which is just 1 cis multiply the angle by 3, and that gives us minus 5 pi over 2. So quick and easy to raise it to the power. All right. Now, this question looks similar, but it's totally different. I'm giving you w to the power 4, and I'm asking you to solve w. So now we're finding roots. I've already raised the number to the power 4. What was the number? With the previous page, we asked, take a number and raise it to the power 4 and give me the answer. Now I'm giving you the answer, and I'm saying what number was raised to the power 4. So it's the opposite way around. So we're finding roots. And to find those roots, we've got a special technique, and we've seen that there will be 4 different options of numbers that I can raise to the power 4 to give me root 3 minus I. So first things first, w to the power 4 is root 3 minus I. I need to change it to polar form. that will be real, imaginary, that will be in the fourth quadrant again. My r value is the square root of root 3 squared plus 1 squared, so that is root 4, which just gives me 2. And my principal argument is arctan of b over a minus 1 over root 3. And that gives you minus pi over 6. So that I can rewrite as 2 cis minus pi over 6. And then when we looked at this section, we looked at the formula that we can generate all our solutions with. Wk is 2 to the power 1 over 4. That 4 comes from this exponent. Cis of minus pi over 6 plus 2 pi times k over 4 from the exponent. And my k values are 0, 1, 2, and 3. And in the section where we looked at that, we saw why we can stop at 3, because when we get to k equal to 4, if we take any further numbers, we're just generating the same complex numbers. So W naught is 2 to the power 1 over 4. Cis, when k is equal to 0, I've got minus pi over 24. W1 is 2 to the power 1 over 4. Cis, k is equal to 1, so I get 12 pi over 6 minus 1 over 6 gives me 11 pi over 24. W2, 2 to the power 1 over 4, cis, k is equal to 2 now, so it's 4 pi. In terms of sixes, that's 24 over 6, minus 1 over 6 is 23 over 6, divided by 4 is 23 pi over 24, and W3, 2 to the power 1 over 4, cis. If k is equal to 3, it's 6, that's 36 minus 1 is 35 pi over 24. There we go. Now, depending on what question you're answering, you might want your answer in polar form or rectangular form or exponential form, but we've looked at converting those in other videos. All right. Now, the next question is, what's the angle between successive roots? So what is the angle between W1 and W0, W2 and W1, W3 and W2, and so on? What is the size of that angle? Now, you can do subtraction. If I just look at between W1 and W0, 11 minus 1 gives me 12 pi over 24, so that's pi over 2. Same for all the other differences, it gives me pi over 2. Another way to calculate it, if you don't want to subtract, and this is also a way to check if you're correct, this is to the power 4, so successive roots will be a full circle divided by how many there are, and that is pi over 2. All right, the last question, and this is just to make sure that you're not getting confused between roots and raising to a power. So take this question down, answer the two questions, and for once and for always be sure that you know the difference. Question 1, we're given w, and we're asked to find w to the power 4. Question 2, we're given u. We have to find u if u to the power 3 is equal to z. So let's look at the first one. W to the power 4. Now I'm given w is equal to minus 2 root 3i. Now we need to change it to polar form first, then raise it to the power using de Moivre's. So polar form, that again is in the third quadrant. I'm favoring that quadrant today. My r value is the square root of minus 2 squared plus minus 2 root 3 squared, which gives you 4 plus 12, which is 16, so that's a root of 16, that is 4. And theta is arctan of b over a, so it's minus 2 root 3 over minus 2, minus pi to get the principal argument in the third quadrant, and that is minus 2 pi over 3. So w is 4 cis minus 2 pi over 3. All right, now we're looking for w to the power 4. One step, it's 4 to the power 4 cis, multiply that one by 4 minus 8 pi over 3. Using de Moivre's. I'm given W, I want to raise it to the power. Now look at the next question. The next question says, u to the power 3 is equal to the z that we're given, minus 2 plus 2i. All right, u to the power 3 is equal to z. So I'm given u to the power 3. I'm looking for u, so I'm now finding roots. I'm not raising anything to the power. It's already been raised to the power. So now I'm looking for roots. But the first step, change it to polar form. That now is in the second quadrant. Our r value is the root of minus 2 squared plus 2 squared. So it's the root of 8 or 2 root 2, whichever you prefer. And our theta, to get to theta in the second quadrant, it's arctan of b over a, so it's 2 over minus 2. But that will end us up in the fourth quadrant, so I need to add pi to that. And then we'll get this value of 3 pi over 4. So u to the power 3, which is just z that was given, that is equal to 2 root 2 cis 3 pi over 4. All right. Now, to get to all my roots, I will have 3 roots. They will look like this. uk is equal to 2 root 2 to the power 1 over 3. That comes from the exponent. Cis. I've got 3 pi over 4 plus 2 pi times k divided by the exponent, which is 3. And my values of k is 0, 1, and 2. So u1. Now this is a bit ugly, but messy. I think 8 to the power 1 over 6 is a little bit tidier. Cis k is equal to 0, so it's 3 pi over 4 over 3. So it's 3 pi over 12. I'm just going to write that, but we can simplify that as 8 to the power 1 over 6 cis pi over 4. All right, u1. 8 to the power 1 over 6, cis k is equal to 1 now, so it's 2 pi, so it's 8 over 4, plus 3 is 11 pi over 4, divided by 3 is 11 pi over 12. That was u0, u1, and u2 is 8 to the power 1 over 6, cis k is equal to 2, so it's 4 pi, 4 in terms of quarters, that's 16 plus 3, 17, 18, 19 pi over 12. There we go. So please make sure that you know the difference between these two questions. Raising a number to a power or already given a number that's been raised to the power and finding the roots. And that's a wrap up of some selected questions, mixed bag of questions on complex numbers. You should now have a better idea of how you're doing on this section.